Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, thanks for coming. My name is John Crum. I'm a researcher here in Microsoft, and I'm happy to introduce my friend Anthony Lamarca, who's the Associate Director at Intel Research Seattle, whose lab is just right across the lake from us. Anthony got his PhD at the University of Washington. Last time Anthony was here, he talked about doing outdoor Wi-Fi based location, and he also talked to the Virtual Earth group about that. And several months after that meeting, that feature actually showed up in Virtual Earth. So just before this talk, Anthony was talking to some people in Windows about doing things on context. So maybe thanks in part to Anthony, we'll see a feature like context show up in a future version of Windows.
You guys got 5 months. That's how long they took. That's why I was impressed. Well,
so take it away.
Thanks for the intro, and thanks for having me. So, so as John pointed out, both he and I actually have been working in the space of location for 4 or 5 years now, and I think we're all actually starting to take a look a level higher. Location is sort of a classic example of context, but there's lots of other examples that are like location derived from sensors using inference techniques. And this whole talk is really about opportunities and challenges in that space. So a little bit about sort of who I am and why Intel wants us to work in this space. So I'm part of a group called Intel Research in general, and our mission statement is to work on something called essential computing. And the first time I sort of heard essential computing, I sort of scratched my head and didn't really like it, because it's sort of like, well, what do we mean by essential here? Are you talking about just the bare minimum, and why are we working on bare minimum, just the critical stuff, or is it essential as in like it's so good that you actually become hooked on it? So sort of essential computing. I got to get my fix, and I realized actually we kind of want both. I mean, we want to actually really try to focus on what is of really high value to users, and deliver things that they really couldn't imagine doing without. I have to bring this device with me because it really. Unlike some of the navigation systems we had before, where you bring your device, but you still bring a paper map because you don't know if it's going to work. You're not sure you're going to want to bother to take it out and set it up. We want this to be so smooth and so high value that it does become essential in our everyday life. And we have four themes that we've structured most of the projects inside of Intel Research. I should say Intel Research is about 100 researchers. So we have our lab across the lake in Seattle, and then there are other labs at other universities and Intel sites. And these are the 4 areas that we see, I think, having the most potential for us to influence the way the technology winds up developing. I mean, there's lots of stuff like compiler technology where it's sort of marching along a nice steady path, and we can get involved or we can not get involved, and it's probably going to work out in a way that we'd like. But in these spaces, I'll just sort of tick through these. So physicality actually was very much what we were just talking about in this meeting, basically having computing systems with effectors that change the environment. Complexity is a really big deal, right? If we're going to make systems that have hundreds of elements, they have to really work well together. They have to be easy to deploy and maintain. They can't be a nightmare. But the 2 themes that my lab is most focused on, and I'm going to talk about mostly, are the top 2, and they're around, I sort of call the me theme, personal awareness, which is having your device sense and infer and be aware of your context and what you're doing, and modifying application behavior and system behavior to bring value. And then of course it's not just about you, but humans communicate, and the way we choose to design technology actually affects how that communication gets mediated, and so that's another important theme. Really, all of these themes fit in really well with our lab's mission, which is working in the space of ubiquitous computing. So, for those that haven't heard this term, this is a research area that's about computing off the desktop in the environment. Small devices, embedded processing, sensing. Where if I walked up to you and said, "What are you doing?" you'd say, well, "I'm making a souffle," or "I'm playing lawn dart with the kids." You wouldn't say, "I'm using a computer." So we have 15 researchers in our lab. but we hire lots of interns and external faculty come and visit. So we usually have a community of around 30, sort of weighted more heavily towards the summer. And our goal is actually to really understand how users' context can be inferred and how it changes over time, and how to use it to push this essential computing vision. So feel free to stop. This is a small group, so feel free to stop me and ask questions at any point. So, I mean, usually people give a talk, and at the end they sort of end with the challenges and say, oh, so here's where I see the big opportunities and challenges. But I actually thought I'd put them at first, because it gives a sense for what I think is difficult about the sensing and inference. There are, we were talking about that just before this talk. I mean, there are actually lots of examples these days of pretty sort of closed loop systems that do some sensing and inference on platforms today. And they're primarily being used for platform maintenance. So, we're using sensors in computers to make the computer a better computer, right? We put lots of temperature sensors on the motherboard so we can figure out which of the fans to turn on. And we turn on the smallest set of fans possible because it makes the device quieter. Or, increasingly laptops have accelerometers so that if you drop the laptop, it can detect before it hits the ground that it's in free fall and park the hard disk, so you've built a more robust disk. And I call those sort of platform maintenance features. Actually, the application is making a better mobile device. But as you look to take sensing and inferring context, and you look to take it outside the platform to augment existing applications or to create new applications, a whole bevy of problems come up. And I think in some more than others, but this is the set of things that I think we're trying to address in our work. And these shortcomings in the existing solutions are why this is still a problem that's pretty squarely in the research domain. And you're not seeing a lot of what I'm going to talk about being sold now. So I think I already mentioned that, deploy and maintaining systems with lots of components, especially if they're inferring and doing modeling to try to figure out what's going on, is not easy. Lots of stuff's been shown in the labs, and for these 8 people in these 6 activities, it works great. But people come in lots of sizes and shapes, and people do lots and lots of activities. And making something that you can go grab off the shelf at Fry's and expect it to work with high probability, I think we're still quite a ways away from that. And there are probably still a lot of customization mechanisms that I think you need to do to have these things adapt to individuals. I'm going to show you artifacts that clearly we're not going to design. We're not going to win any industrial design awards. But even still, past systems that have successfully done sensing and inference have had serious wearability challenges. I'm going to talk about that a little bit. Systems that infer things about your health and your wellness and your emotional state and your social network raise privacy issues, I think, at a level that haven't been raised before. I mean, in the past, there's a lot of your visa bill is this really, really private piece of data that if it got on the internet, it would be a really bad thing. And I think that's going to look tame in comparison to the types of things that your personal devices will be able to infer about you in the future. The sort of the elephant in the corner of the living room that most of us just try not to talk about is power, because it's a huge deal. The reason your cell phone lasts 5 days now is not because we build better batteries, but just that the cell phone is sort of, for the most part, off almost all the time now. And if you do turn on features like Wi-Fi or GPS, your 5-day cell phone drops to like 4 hours of life. So power consumption is a really big deal. Doing the things we're going to show, but also doing them in a way that doesn't impact the high standards we've come to expect from our devices. And finally, sort of adding this, once you sort of get all this solved, context is this shoe that's been sort of waiting to drop for 10, 15 years in UbiComp, and lots of people have worked on sensing it, inferring it, and storing it, and shipping it across the network, and sharing it with others, but actually showing the real-world value of it. How can I build a better word processor? How can I make a cell phone interface for calling something? How can I make that richer and better with context? Actually, in my opinion, that loop hasn't actually been closed, at least to my satisfaction. So build some real applications and actually try to quantify the value that the sensing and inference has on a non-context-aware solution to the same problem. Any questions? John? Good. Okay, so I'm going to talk about, it looks like 8 projects. Actually, I slipped one more in right at the end. I got a slide literally 10 minutes ago that I threw. That's the worst slide in the deck. I'm going to talk about 8 or 9 projects going on in my lab. I sort of broke this into 2 clusters because there's sort of a common story that kind of follows from the first one and then into the second. These are all ongoing projects. They're all happening in our lab jointly between our lab and external collaborators in primarily the University of Washington, but other universities as well. And there really are small attempts to address some of these challenges that I outlined on the slide before this. So if we're gonna look at context-aware computing, we pretty quickly, as in, well, it took us like 4 years, realized that we needed a decent platform for doing exploration of context-aware applications, something we could reuse because building hardware, as some of you know, is it's a challenging thing. And so we wanted to build, since we don't have a lot of resources, really the worst platform we could that would let us do some real-world experimentation. And so we have a set of requirements on what you'd actually need for a mobile platform, because that's where these scenarios get more interesting, that will let us actually do some sensing and inference. And we actually, what I'm showing here are examples of systems that we either built in our lab or in Intel Research in general. We didn't build the IPAC, but we did use it. That didn't work in the sense that they were missing had some key shortcoming that didn't let us collect the data we wanted. They kind of got in the way of the user experience, where we went and we did an application, and the high order bit was not your application enabled me to do this, but your device sucked. And what we came up with was this set of requirements, which was we needed something with a bunch of sensors, because we do want to enable people to do things. We didn't want to sort of constrain it and say you can only do accelerometer-based studies or microphone-based inference. We needed a processor to do real-time inference. So we tried a couple of platforms that just sort of took the data and just shipped it right off or just logged it. And it turned out we wanted to embed the inference on the platform itself. We need to be able to do wireless networking so we could talk to other devices, because we weren't going to build something that actually had a screen in it. Lots of storage for online applications. There's a minimum battery life of 1 day. And this I really want to say that this is really based on a research platform. In reality, you couldn't sell a real product probably that got away with this. But this really had to basically wake up, put the thing on in the morning, and then it should really run until they go to bed at night. So 16 hours was sort of like a bare minimum battery life, which you don't get from lots and lots of the existing research platforms you go try. And it had to be small enough that you could actually wear it, put it in your pocket. It shouldn't be a big nasty thing. Now, I should predicate all of this with, there are application domains. If you're deathly ill and we design a solution that will help you stay alive, it doesn't matter if it weighs 20 pounds and is covered in fish hooks, right? You're going to carry this thing with you because it's really this ultimately high value application. A lot of what you look at in UbiComp are small lifestyle, I would say sort of low to medium value applications. And I don't mean that in a bad way. This field has the potential to enable dozens or hundreds of these low value applications, but because of that, they tend to have to have a low cost. People aren't going to bring it if it is actually a serious inconvenience. So we really were trying for sort of minimum user cost and distraction here. So this is the platform that we developed. It's called the Mobile Sensing Platform, because at Intel you have to give things really sterile names like this. We couldn't call it something like Aphrodite or something like that, because there's something else called that at Intel. So the platform has 7 built-in sensors. It's got, and honestly, this was just sort of everything cheap and small and low power that we could find that we threw in. So accelerometers, a 2D compass, barometer, humidity, visible light, invisible light, temperature. Actually, didn't include the microphone. It has a microphone in it as well. And for processing, we actually put in a 400 megahertz X scale. So this is sort of on par with what you probably would have run Windows 95 on. So this is a pretty serious processor for doing embedded inference. There's a Zigbee and a Bluetooth radio, and then to support experimentation, we included an extra serial line if you wanted to connect something that just spewed out serial, and we even left some GPIO pins available if you want to connect some extra analog sensors to it. And it's got a little flash slot, so you can actually put, add flash cards to it. We have 2 gigabytes right now, but bigger will be available. And then we built another add-on board to support some experimentation with inertial sensing, because the accelerometers actually alone weren't enough to do what we wanted to. So 3-axis magnetometer and gyros, they're not part of the main thing, because it turns out they're a lot larger and they draw a lot more power, so they're potentially interfering with some of our requirements. And the idea is that this was going to be,
What do the buttons do? Buttons you can press on it?
This button is currently not connected to anything. We have a button board, and it connects, and the system can tell that it's being pressed, but it doesn't actually do anything. Our idea was that we would use this to sort of if you wanted to say do some active learning stuff, where you wanted to say every time you get in an elevator during the day, just tap this button once, and we'll grab a 20-second window and try to train up models. I mean, we just included it for just as an input. We haven't actually used it yet. So this is the platform that you're going to see some of our experiments with. I guess, hey, dude, I guess I should also say that actually inspired by the SenseCam work at your Cambridge lab. We have a batch of, I think, 100 of these that we're assembling right now that we're going to be giving to academic researchers in sort of a very, very similar sort of call for proposals. What would you do with these sensors? And we're going to sort of give them away to try to seed some seed development of interesting applications or inference techniques, or really whatever whatever they're interested in. So I should say, actually, from a systems perspective, the system actually runs, because it has so much memory and so much processing power. It runs full-blown Linux. So the Bluetooth runs in RF comm mode and PAN mode, so you can SSH into the thing. Somebody even ran a little Xserver on it, which I don't understand at all. But from a computing and programming perspective, this is it's a far cry from TinyOS. It's really quite a civilized little environment, and we've even got a nice little reconfigurable XML thing where you can actually say, I want these sensors at these frequencies, and please apply these features, and then stream them over Bluetooth. And you just sort of set up this one XML file. So you actually don't wind up even having to program much on the device itself to do something non-trivial. So the first example I'm going to show you of something that we've done in our lab with this device is everyday activity inference. So it's been known for a long while that if you want to infer everyday physical activities like walking, climbing, sitting, lying down, brushing your teeth apparently, that you can infer this by putting sensors on people's limbs. So if you actually wind up instrumenting the extremities, you get a lot of kinesthetic data, and it's actually quite easy to figure out what people are doing. Now the problem here is that this is great if you're if you want to instrument the football player and scan some of his data for the next Xbox game. But in terms of our everyday life, I mean, you can't say you have to wear these shoes or you have to move these little clippies from your shoes every time you want to do this and wear these special breaks. People just aren't going to wear it. So there's actually a research challenge to say, well, if you took all those sensors and you pulled them into a single cluster, so if you were going to actually put all the sensors on your cell phone or all the sensors on your ultra-mobile PC, could you actually infer the same types of activities? So that's sort of the research challenge. And so what we did was take the MSP and run some, frankly, pretty standard machine learning techniques. And what we found was that we could run, we could run embedded inference and get about 85% accuracy for a class of around sort of 10 to 20 everyday activities. So, yeah. Go ahead.
How did you pick the activities you wanted to infer?
That's a great question. So we've done this twice. So there was an initial, I think, pervasive paper where there was this set of activities: up and down elevators, driving a car, jogging, walking upstairs. These were chosen by Tanzim. I have no idea why. She hired some grad students to go out and do it. The second batch of activities we did were driven specifically by an application. So you'll see where we did a fitness application where we actually did surveys and said, basically, what are the top 15 fitness activities people do, and we basically just chose those that we knew we could infer with the MSP. We can't infer swimming because the device will short out. You have to take it off. We couldn't infer weight training because there just wasn't enough regularity to it to actually infer. So in that case, we had, I can actually show you a little demo of it. We actually had things that were physically quite similar, like being on an elliptical trainer and being on a Stairmaster. They're actually quite difficult to discern from each other. So the accuracy varies, definitely, especially pairwise when you look at the different activity sets. But that's where we came up with.
85% accurate could mean any of a number of different things. For example, if you're sitting 50% of the time and you're 100% accurate at predicting the sitting, you might be 70% accurate at everything else. How is that number calculated?
That's a great question. So in this case, I believe this 85% came from, I think it was a fairly uniform distribution across all the activities. There was no sort of, this was a controlled experiment where we had 20 minutes of walking, 20 minutes of sitting, 20 minutes. The specifics are in the paper, but there was no one activity that, like, sort of human life dominated. It wasn't like we said, there's 12 hours of sleeping in there every single day for you to actually compare against. So there was no one dominant activity, and the paper actually has precision and recall numbers. There's a little more specifics on this slide. So algorithmically, these were sort of boosted decision stumps with some hidden Markov models for doing some temporal smoothing. And this experiment, the one the 85% in that graph came from, and these data came from, was a small study with 8 different activities in 7 hours of labeled data. So it's not a whole lot, although anybody who's done this knows that actually sort of trying to label exactly what you're doing second to second and getting it accurate is it's often really challenging. And we did do per-person holdouts for the evaluation, so it wasn't the case that you were training and testing on yourself, which is good. And what they actually did was, and this was really to try to say, well, gee, not only, I think we talked about this in the last hour, not only do I want to put all the sensors in a single cluster, but I might not want to actually dictate where people carry that device, because some people put their cell phone on their waist, some people put it in their pocket, some people put it, in their handbag. And so they tried a few experiments where they had data collected from 3 different data points. In this case, shoulder, waist, and then something wrist for like a watch form factor. And we did both testing and training on a known location, so we know this thing is a watch, or training on a generic model that might work in multiple locations, and then testing it. And you can see, not surprisingly, the accuracy drops when you build a generic model, but it tends to sort of be in this space. This is not necessarily fabulous. I mean, you definitely, if you're going to do any real application or system adaptation, I think you need to drive this number higher. What is reasonable here is this is really doing, like, I believe quarter second to quarter second estimates of what you're doing. So really, the system gets a quarter of a second worth of data, and it has to figure out what it thinks you're doing. In reality, people do things for sort of semantically meaningful amounts of time. You don't get in a car and drive it for a quarter of a second and then get out. So if you've been driving in a car for 5, 6, 7 minutes, you probably didn't immediately transition to a bicycle, right? You might be getting out of the car, but chances are, you're still doing the same thing. So as you'll see in this next application, if we do try to actually take these individual inferences and chunk them into semantically meaningful things, we can drive this number much higher. But I think there's still a lot of room for this base activity inference to get more accurate by doing things like, and John and I have talked about, like including location in a notion that, like, one of the baseline sensors is not just some kinesthetic stuff, but where are you? And if you're in the middle of I-5, chances are you're not brushing your teeth. Is that a reasonable answer to your question? So here's the first application that we're actually using. This is sort of a real attempt to extract end user value and give the user something that they didn't have before, using a system that senses and infers. And I should say actually that John Froelich, who is working for John Crum this summer, actually wrote, I would say, the vast majority of the code running behind this application in our lab last summer. So if you have any questions about Windows Mobile, he's hell on wheels. And in this case, the challenge was to try to use on-body sensing, and in this case, we're throwing in a personal mobile ambient display to actually try to encourage regular physical activity. So we're trying to use computing to persuade people to modify their behavior. So difficult challenge, but a good opportunity. And our approach was to take the MSP and put a classifier on it that was trained to recognize fitness activities, things like being sedentary versus walking versus running versus using a cardio machine, and then couple it with, in this case, an application actually running on a Windows Mobile 5 smartphone. And we used the background screen. We actually modified it to show this flower garden. I'll tell you a little bit more about that in a second. But the idea was there was really sort of a two-part thing going on here, where the MSP was basically collecting data about your physical activities with some opportunity, to actually manually journal things that you didn't do with the MSP on, like swimming, or if you just plain left it at home, and then actually using the phone as the display to communicate some sense of awareness. And the idea behind the display was to subtly and in a positive way communicate what you were doing. So the participants would establish some goals, saying, I want to get out and walk 3 times a week, and I want to do at least one cardio thing for at least 20 minutes in a given week. So there were goals, and the different activities that were inferred were represented as different flowers, and the flowers bloom through the week, and you meet your goal, you get butterflies, it's all positive. The data suggested that if we started with something negative, you could think of lots of clever examples of ways to wag your finger at a user that they don't like it. So this was the approach we tried. And actually, the diversity of activities, so actually individually calling out things like walking and stretching and cardio, actually came from a previous study we'd done last year or the year before on pedometers tied in with a not dissimilar phone interface. It turned out this was a social application where people could communicate results. So we were trying to look at the effect that people's social networks had on encouraging things. And we found that actually, I guess not surprisingly, people did what they were incented to do. So we saw messages go back and forth saying, I'm so mad I went for a run and it only gave me 4,000 steps. If I'd walked the same thing, I would have gotten twice as many. Or don't go up hills because you don't get any extra credit for that. So we really made an attempt in this case to try to capture a wider range of what people were doing and communicate it to them. I would say probably part of the other motivation for this display was, you'd have this phone and you'd be pulling it out at various times to make phone calls or let somebody talk on it. And we didn't want, we wanted this, ambient display that you understand what it means, but there is some degree of privacy. Someone just looking at it would know, obviously, something interesting is going on, but they wouldn't be able to directly infer that you were fat and lazy this week.
Apparently you forgot to put in the sweat sensor.
Huh? Yeah. Well, that's actually, there are devices by companies like, I think, Body Media that you wear on your arm, and they do have a galvanic skin response sensor, and they use it for lots and lots of stuff. It's much easier to infer exertion level, which we can't get. We can't tell an easy run from a hard run without knowing more about you. But yeah, the GSR is a big sensor for those guys. So we just finished, like a week or two ago, a 3-week field trial, kind of a pilot study, just to see if we're even in the ballpark on this. And the results were positive. I mean, there's a couple little tidbits we pulled out, even though we haven't actually done the data analysis. The person building this application was very sensitive to people criticizing her with the flowers, saying, but men don't want flowers. They want, I don't know, muscle cars or bikini clay. Yeah. And she says that I like my flowers, but she says that the men really like the flowers, and there's a whole thing here about small rewards that don't necessarily have a lot of sort of monetary or tangible value. The gym that, if you meet your goal and you fit their little exercise contest thing, at the end they give you a T-shirt. And the T-shirt costs them a couple bucks, but you prefer the T-shirt to them knocking $50 off your gym membership because it's like this badge and you can wear it, and it really sort of transcends the actual sort of monetary value of it. And then we saw, at least glancing at the data initially, some evidence of that. This one I actually found interesting. This really was our first experiment with a device that does some sensing and inference. So from a user's perspective, and we did actually ask some questions of the users, which we haven't analyzed the data, which is, well, how did you think this thing was figuring this out? What did you think it was doing? Because people often create much more interesting scenarios and motivations. I did a press demo where they said, well, but then the device hedged its bets and said 89% because I might have been doing this, and there was no hedging going on. It was just a really, simple Bayes filter. So we were curious as to what people were going to think about a device that was actually inferring, and this one I actually found surprising that we knew that journaling, putting things in manually is a pain, right? You're not going to go, especially if it's something you do 2-3 times a day, you're going to lose interest really, really quickly. And so the automatic was going to be more convenient, but we actually saw evidence that people preferred the automatically journaled things because they found it more rewarding, that actually this was something that was objective and had nothing to do with their own biases, that it actually, it saw that I walked 30 minutes and there's no doubting it. This wasn't me thinking maybe it was 30 when it was really closer to 20. So actually the unbiased, even if not perfectly accurate nature of it actually was seen as an advantage. And then I guess this isn't surprising, but the combination of having something automatically infer with the opportunity to actually go back and correct things, because errors are potentially an issue, that seems to be part of the secret sauce. Completely automatic, I think, is unlikely to work until the inference gets near perfect. And manually journaling, we already know, and we have tons. We've probably all tried to set up a blog or do a fitness or a food thing where we give up after a week or two when we get kind of tired of it. That this combination is potentially where the secret sauce is for systems that do this type of inference. So the researcher, I should say, I've been sort of putting the research lead down here for the person that's leading the effort. If you have follow-up questions, you can contact me or contact them. But the research lead who did the physical activity inference work that we've actually been evaluating in this UbiFit application. Oh, I should show you a little demo here. So this is, I'll just turn this on. So I'm going to put on my MSP. So let's see. So this is, just to show you that this actually works. So this is the this is one of the UbiFit MSPs. So this is running the classifier that's being used to drive the flowers. But in this case, I'm sending it to this little display here, and this is what it thinks. It thinks with very high likelihood that I'm standing or sitting right now. Let's see if it thinks I'm walking. Yeah, so it's reasonably responsive. And then for UbiFit, we're lumping it together into these 15, 20-minute things, like saying, oh, I see that you did a walk of at least your minimum 20 minutes. Let me see if I can get some running. I'm not going to get a flower for this. But so this is sort of the quality and type of data that you get from a system like this, but definitely well beyond something like a Nike pedometer. So make sure I'm actually in here. So the same researcher who did the physical activity inference was interested in basically saying, well, can I push this into another domain? So same types of features, same types of statistical modeling techniques, but I want to look at it in a completely different domain. And in this case, she's actually looking at inferring people's social networks and the roles they play in them, both statically and even potentially dynamically. Like, well, this person now seems to be dominating this conversation for this reason. And this is coming from the psychology literature that says that to actually infer things like social role and people's social state, you actually emotional state, you don't need to actually understand what's being said, but more how it's being said. What are people's physical pose? How is the turn taking happening in the conversation? What volume are people speaking at, and how shortly after one person stops speaking do they get interrupted by someone else? And that those cues are actually enough to infer quite a few high-level semantic things about social role. And from an application perspective, there's the potential to do things like health for diagnosing some cognitive disorders. So both autism and depression are apparently very, very highly indicated by the way people interact socially, especially in terms of the trending. Outside the health space, you can imagine in the social mobile computing space, things like dodgeball or instant messaging or this ambient orb, that this is the type of data that you might want to communicate for things like interruptibility or people's state. And then you can even imagine taking the data that you learn, the models that you build, and taking them completely outside of this type of mobile system and using them for something like improving virtual characters in augmented or virtual reality systems. So this is definitely ongoing research. Tanzima actually had interest in this for a couple of years, and I don't know quite how she did this. I don't know if you were involved in this, but she actually got the incoming graduate class of the last 2 years in the computer science department to wear MSP 1 week a month for the whole school year. So she could then potentially take the features that she wasn't storing any raw audio, but storing features in the audio, to basically try to infer the social network and actually watch how it evolved and how relationships changed. So there's 2 years worth of data. It's like 800 gigabytes of feature data. I think she got the data by just giving them a cell phone at the end of the year. Is that what you got out of it?
Pocket PCs.
Pocket PCs. Grad students are so cheap. And I know she's done some social network construction and some conversation segmentation, but I think she hasn't gotten into the really interesting part of doing the dynamic role stuff. But it's scary from a privacy perspective, but potentially valuable and interesting. And then I think the last thing I'm going to talk about related to the MSP is pedestrian navigation. I think I sort of made a promise to myself that I wasn't going to talk about anything to do with location. But one thing we did discover doing the location work is that when you take things like the navigation work that John's interested in, you put it on a mobile device. From an HCI perspective, there's a whole set of challenges that just you don't have in a car environment. And car navigation is great because the device is bolted into the dashboard, the user is strapped into the seat, you know which way the car is facing. If the car isn't going straight and it's going sideways, the user definitely is not in the navigation type mode. And if I give you a device with a dot on a map, people they'll stand here and go like this. And So we want to investigate basically how we could make that better by having the device be really sensitive to the direction that the user is facing, the pose that they're actually holding the device in, and I had a demo and I didn't bring it in because the researcher, in this case Jeff, unfortunately had something else to do with it. But it turns out accelerometers alone are insufficient. This is honestly one of the main reasons that we actually designed the gyros and the magnetometers. And he has a demo that actually has, in this case, Google Earth. So we're just sort of connecting it up directly. You could imagine this being a platform feature that would actually figure out direction and pose, where the interface actually scales. So as you actually tip the device up, it tips to the horizon, and as you move, it moves perfectly. So you could, like in an indoor navigation space, pull your device out and hold it up and say, oh, right, that's the food court we're going to because that's actually where the dot is. It's very compelling. If any of you get to come to our open house in September, you should make sure you play with this demo. So that's the last bit I'm going to talk about for, I think I would say for sort of mobile sensing. I'm going to tick quickly now through a different series of projects, and this one is largely based around the application of long-term care. So, and for people who've seen the first 2 or 3 of these slides, I apologize. I'll go through them quick. So now we're talking about assisted living, and it turns out that one of the most important things in an assisted living environment is actually not actuating and sort of doing something to the person being cared for, but actually figuring out whether they are successfully dealing with the activities of daily living. So literally things like, did they get themselves dressed today? Did they manage to clean up in the morning? Did they make themselves breakfast? Are they hydrating properly? Can they use the heating in their home? And this is really time intensive. Not very accurate because you have maybe, in the case of someone still living in their home, you have somebody come in maybe 20 minutes a day, check them out, and so you say, did you eat this morning, hon? And they say, yeah, sure, but you don't know how accurately they're reporting it. Or you look at the dishes and try to make a guesstimate as to how many meals they ate. And it's expensive, and that's care you could be spending for something else. So for us, this has had sensing and inference written all over it. The bar is low in terms of where the current accuracy is. Screaming for a technical solution. So we chose this as a problem to work on. And in this case, it's a little different in that we actually did the formative work first. So before we actually tried to build any technology to make this happen, we did a study, and this is pretty old. This is from 2004, so this is close to 3 years ago. But we basically said, gosh, if you could infer this type of data with high accuracy, what would you do with it? And so So we built a display motivated by Beth Mynat's little ambient display, and we actually deployed it in the homes of elders for 3 weeks. Not in the homes of, I'm sorry, in the homes of the care network of elders. So in this case, this person whose pseudonym is Rita has this network of people that provide for them. They've got the seemingly ubiquitous adult child who has really made huge sacrifices in their life to take care of them. They've got other siblings. They've got people they know they can call on if as a fallback if something goes wrong. And we deployed these displays in their homes and the elders. And we simply called the elders to find out what it was they were doing. What did you eat? Did you take your meds? Who came and visited? And we used that to populate the display. And the big surprise was that we found really high value propositions for people across the network. That for the people that drastically changed their life to take care of the elder, they felt much more relaxed because they knew other people were getting the data. They were not the sole connection for this person, so it actually let them feel like they were not such a critical link in the chain. For the blue people, the significant contributors, it turns out that they, for the most part, thought that they were doing as much work as the person who is in green here. This graph is actually showing the length of the line is physical distance they lived from the person, showing how far they had to drive, and the size of the dot was how much work they actually did. So the blue dots in this case came to appreciate how much work the green dot was doing, which they hadn't realized, and they would see that by the visits in the display. And then the peripherally involved actually liked it because they actually had something to talk about. They actually now understood what was going on in this person's life, and they didn't have to feel like they were so disconnected, so they could call up and say, oh, so Aunt Mary came and visited, how's it going? So we had a really high value proposition. All of the elders wanted to keep it. They all pulled out their pocketbooks and said, please don't take these devices away. It's made such a big difference to me. And this was before we even looked at the value that you would get from actual professional care providers having this type of data for the patients they were caring for. So to do this, we decided that we were going to skip the whole vision-based system because we didn't have any vision experts, and it seems like it's difficult and has lots of privacy issues. And the key insight here was, these are movies from, these are screenshots from the cheesy Invisible Man movies. And the key observation here was that what you're doing in your daily life is largely indicated by the objects you interact with. If there was an invisible man in your kitchen making an omelet, it would be obvious, right? You can't see the person, but you see the refrigerator door open, you see the eggs walk out, you see the omelet pan, you see the whisk, you see him go over to the stove. And then if we can actually just track your object interactions, we can, with reasonable accuracy, figure out what activities you're doing, especially in a home type setting. So the system, the idea was to pick maybe a couple hundred, eigen objects in your home and put RFID tags on it, and then make a wearable RFID reader. So in this case, this is a short-range inductive tag system. It's got sort of this fairly ghastly bracelet. We have the next generation bracelet has a flexible antenna. It's much smaller, but it's got a range of about a foot. So you can sort of imagine this sort of invisible globe around your hand, and as you sort of pick up different objects, you actually get reads off of it. And of course, if you took your hand, you dug around in a drawer, you might get 8 or 10 or 12 reads. But the statistical modeling that we did to represent activities as interactions of object touches proved to be pretty resistant to that. So if you were touching the egg carton and the microwave handle and your little 2-minute egg thing, you're not washing the car, you're not cutting the back lawn, you're probably making yourself some sort of food. And the sort of doubly groovy thing about this was that because we were primarily building our model based on really interaction with nouns, because it really was just object interactions, that a lot of the data that would be required to actually build a model of an activity is actually out there on the internet already. So you can go to ehow.com and it'll tell you how to make a 2-minute egg. It'll tell you how to change your oil. And you can actually take those web pages and in the order of steps, extract the nouns, put them together, and their models aren't perfect, but they turn out to be pretty reasonable. And in this way, we managed to build a database of 40,000 activities, which is usually about 39,998 more than most research systems actually have in terms of modeling activities. So let's see, I'm going to close quickly here. So we did an evaluation where we took some people and had 100 objects in the home. we said grab sort of 12 of these activity cards and put this bracelet on and go do those activities. And the computer made a guess at it, and of course we have the cards at the end so we know what activity they did in what order. And so these are precision and recall numbers. And not surprisingly, it worked reasonably well. I mean, we had challenges when people did things with the hand that didn't have the bracelet on it. But what I would say sort of the high order bit to take away from the evaluation is that the blue dots, which were existing research solutions in this space, were really point solutions. That if you wanted to infer, medication taking or washing up, people built specific systems that had custom sensors designed to that one activity, and that we sort of in one swath with sort of a not exactly perfect solution, but pretty reasonable, kind of with a shotgun spray, kind of got them all. I think it says something about graduate students that there have been 3 systems for inferring making snacks. And so the challenge now is to actually show that this would really work, that you could actually put it in an actual assisted living setting, and that, I mean, this kind of comes back to the beginning, that what we could infer would actually reduce care burden and actually has real value. So we have a study that we're doing now across Intel and Washington State Aging and Disability. We're doing this in Providence, with Providence Hospital and Swedish Hospital. So we're looking for a 20-person deployment by the end of the year, and we're sort of busy hardening everything. Sort of watch the space. If you come to the open house, you can get more information on this. We have a little mock apartment in our lab where you can actually play with the stuff and see how it works. If I was going to sort of throw rocks at this project, yeah.
How do you record ground truth information?
How do you record ground truth? So like in this study, we had the actual card. So the people basically, thumbed through, pulled out 12 random cards, did the activities, and said that's the order I did the activities in. For some of the experiments, like the one in the PI's home, he just had a camera that ran, in his house recording video. For the real, for the real elder situation, we're considering something like the SenseCam, where we might take a little portion of the study and have them wear a little wearable camera that faces out and takes a picture every 60 seconds, less of a privacy issue. But in general, figuring out ground truth is a huge issue in these inference systems in general. It's quite hard. Right, so if I was going to criticize this, I'd say that's all great, but if I leave my bracelet off, the system goes completely blind, and I don't learn, I don't learn anything. This thing is absolutely dependent on having that. And it turns out there's an entirely different kind of RFID system that works on UHF, and these are long-range tags that can read at distances of approaching 20 feet now. So I think the clever idea here was that one of the researchers in the lab realized that an RFID tag has to basically collect up enough. Everyone's sort of familiar with RFID tags, right? It's Walmart container shipping. That an RFID tag actually has to harvest enough power from the reader to charge up a little backscatter communication module and actually send its 96-bit ID, back the 20 feet. And in the grand scheme of things, we tend to think of radio as being a relatively power-expensive thing. And there ought to be enough power in that tag to do something beyond just sending the radio, like powering a small microcontroller, potentially looking at the value of a couple of sensors, maybe even working a flash interface, and that we should be able to actually make a full-blown computer system, albeit extremely low power, from what's actually basically already being collected from an RFID reader. So we call this WISP, which is basically wireless identification, which is what the RFID tag did already, but also turn it into a sensing platform. Now, tying this back to the assisted living situation, now we have the potential to get rid of the glove, and the kitchen may have a long-range RFID reader in it, where it is aware not only of the fact that there's a Diet Coke can that's in the kitchen, but in fact that it's being moved from the accelerometers, that its temperature is changing, that it's being tipped at a certain angle. So now you can actually lose personal identification, which you would have with a bracelet if it was personal. But you can now sense object interactions, sensors on the objects, and do it in a completely with the people completely uninstrumented, which I think is really exciting. There are other cool applications you could do with this. The the flash that we actually have on this little WISP module, you can actually still read it from a computer, so it's still sort of regular flash. So it lets you do something cool, like if your laptop or your mobile device is done and turned off completely, so it's completely powered down, you can actually still introspect it with an RFID reader, and by sort of especially with like the Gen 2 implementation that can return quite a bit of data in a read, you can actually find out things like, what are your registry settings? Do you have the latest patch? As you walk through the gates in the middle of, at the front of the security thing, it could actually, figure out if your system has the latest security and virus profiles updated, and if not, beep you a little alert saying, you need to update today. So I have a little video of showing this. So this is I think the first one of these. You'll have to excuse our fantastically high production value on the video. I think he's operating the zoom with the other hand. So this is a totally battery-free sensing platform. So this is like 3-board stack. We have a tiny little version of this. I was going to bring one to pass around, but I lost it. So this is the type of device that's suitable to be completely embedded in plastic. It's got no battery. It's harvesting energy from RFID, so there's no need to ever take it out and do anything with it. And this has a 3D accelerometer in it, so he's showing reasonable response rate. I mean, this is not the RFID protocol doesn't provide a huge bandwidth, but more than enough to communicate the sorts of basic data that we'd get from a sensor. And then I'm going to say 3 seconds worth of about this. This is that same researcher's next project. He's working on personal robotics, so basically trying to take the sensing and inference that we've done for people's devices and try to use it to take a robot into an unstructured environment. So robots do great in factories where they know exactly what they're picking up and exactly what they're sticking in. They do it over and over again, but could you take that same manipulation technology and by adding lots of sensing and understanding of its environment to the robot, could you get it in an unstructured environment where you could say something like, go get all the coffee cups in the house, and it could actually go figure it out. So not so much a manipulation challenge as much as an understanding what needs to be manipulated and how. So I'm going to finish because I think I ran a little bit long. Right? I mean, I think context is a great challenge because it's going to prove what we do already, but it's going to drive new application domains. And I think there's challenges throughout the whole stack, from sensors and the platforms, all the way up through trying to actually use them in high-value applications. And how do you communicate uncertainty to users? And how do you get people to actually, understand what the system's doing and form a relationship with it? I think I'll stop there.
We have a little bit of time for questions, if anyone has one.
With the MSP, what's the average battery life?
So this one, so the answer is it depends. So running the inference for the physical activity stuff with the Bluetooth on going full tilt is about 16 hours. It could be made better. I mean, I think it actually has quite a reasonable sized battery in it. So I think if it was running in a reasonably power efficient way, you could probably go a few days, but we just did not achieving it.
How much does it cost to manufacture?
I mean, a huge amount, like 10 times more than it probably should have cost. I think with the cases alone were like $175 each.
Most of the room in the case is for the battery too.
I should have brought a naked one. I usually do. How much did it cost?
Even the algorithm that you're running might have a potential cost of the battery life. You're switching out different features that you're extracting or different.
I think they cost us about $750 each to make, but that's in like unbelievably small quantities. Like we're actually sending them out to a custom stuffing house and everything. There's nothing. I mean, I think the estimate is, if you were going to embed this in a laptop or in a smartphone, it's a few dollars worth of sensors, and we're largely replicating all the pieces that are in existing platforms already. I should say, I mean, the real thing is that all of these sensors should be the set of sensors we determined to be useful, because we threw in lots of them, should be in the cell phone. And the idea is this sort of helps us figure out what really should be in the mobile platform.
The newest Nokia has infrared, ambient light detection, accelerometry, and some of them have GPS now too. So you're seeing sensor fusion in cellular technology.
NFC too.
Yeah.
The near-field communication. Yeah, I mean, I think in a year or two we're going to stop making our own platforms because there'll be more. Just the HTC smartphones that we have didn't have the sensors in them, right? Or we would have just been using those because they're great platforms.
Well, thanks again.